So my name's Stephen Horns, and this is my talk, .NET Data Security, Hope It's Not a Strategy. So first of all, thank you for having me over here in Sydney. It's an amazing city. I've flown over from the UK, so it took me about 30 hours to get here. So I'm still awake, just. Okay, so a little bit about me. So I'm the co-founder and CTO of a payments company in the UK called LadderPay. So we aim to make business and consumer payments easier for our customers. And as well as that, I also, for the last 3 years, I've been offering courses for Pluralsight over in the States. So a few supplemental materials just before we start. So we're going to cover quite a lot of ground very quickly in this talk. So if you don't grasp all of the concepts straight away in the talk, that's absolutely fine. Treat it as the art of the possible. But I've got some other resources out there to help you. So first of all, there's my course, Practical Cryptography in .NET, that's available on Pluralsight. Is everyone a Pluralsight subscriber here? Quick show of hands. Quite a few of you. For those of you who aren't, I've got some cards at the front there which give you 30 days free access to the library. So if you want to try it out and watching other courses, then help yourself to a card there. So this course will basically walk through what we're doing in this talk, but in a lot more detail, and it kind of holds your hand and goes through the code demonstrations at a much better pace. I've got a second course called Play-by-Play Enterprise Data Encryption with Azure Revealed, which is all about taking everything we talk about in this course, but then using the Azure Key Vault to protect all of your encryption keys. So it makes quite a good supplemental course to what we're talking about. If you go to the GitHub page listed there, I've got all of the source code from my course available for free. So everything we're talking about here is in that GitHub repository, so you don't have to code anything if you don't want to. You can just steal what's there and use it and bend it to your own will. And also, the slides here up on GitHub as well, so if you want a copy of the slides afterwards, just go to that address there. Okay, so why are we here then? So I believe that as developers, is basically your responsibility, or you have a big responsibility to your employers and to your customers to protect their data. So we're in a society now where data breaches are becoming even more common every day, and the people that can really help prevent that is you guys working in your teams back at the office. So for many years, companies tend to think, we'll just cross our fingers, it's not going to happen to us, we're too small to get hacked, or, we've got all these brilliant firewalls and all this impenetrable intrusion detection systems we've got, no one's ever going to hack us. Well, guess what? It happens every day. So nobody's immune to it. So it's up to us as developers to try and put better security into our systems. And as the course is named, hope is not a strategy. So just hoping that you're not going to get hacked and have all your data stolen from your databases isn't a good strategy going forward. But unfortunately, the reality of the world is with increasing project budgets, security always gets pushed right to the bottom of the pile, so it's kind of up to us to try and make sure that doesn't happen. Okay, so what's this talk not about? So this isn't a deep mathematical talk about how encryption algorithms work, you'll be glad to know. So we're not going to do lots of complex maths, because I'm rubbish at it. And we're not going to talk about cryptanalysis either. So cryptanalysis is kind of the art and the science of breaking encryption algorithms, so that's not what this talk's about. What this talk is about people like you and me who work on teams of developers for organisations building enterprise systems. So this talk is really aimed at looking at what's in the .NET framework and using those tools to our benefit. So most of these sort of code snippets we're going to look at are sort of from the more traditional, I say in quotes, .NET framework. So typical, server-side APIs, WCF web services, all that sort of thing, or client code. So if you do WinForms, WPF, or anything like that, then this stuff's all very relevant. So in the .NET Core world, if you're using .NET Core 1.1 and .NET Standard 1.6, you're kind of out of luck. So most of the APIs we're talking about are not included. But luckily, 2 days ago, .NET Core 2 was released and .NET Standard 2, and you'll be glad to know that we have feature parity with all the APIs. So if you're in the .NET Core world and you're upgrading to .NET Core 2, then you're in luck. And what a good time to release .NET Core 2 while we're here at NDC Sydney. So I've spent the last 2 days upgrading my code base. So whilst what we're talking about has got a very Microsoft focus today, actually the concept of what we're talking about is kind of transferable across different systems. So if you work in Java, PHP, God forbid, Python, Node.js or anything else like that, then all the concepts that we're talking about are transferable. It's just obviously the APIs are different. So is everyone here a .NET developer? Okay, pretty much most of you. Anyone going to admit to being a PHP developer now I've said that? Sorry. I apologise. Okay, so we're going to cover quite a bit of ground. So what we're going to do is we're going to break it down into a series of abstractions, I guess, because we love abstractions. So first of all, we're going to talk about random numbers and why they're important, because they kind of underpin everything that we do in cryptography. We're then going to look at hashing and HMACS, or that's hash message authentication codes. Then we're going to talk a bit about secure password storage and sort of what's a good technique and what's not good techniques to use. Then we're going to look at symmetric encryption, so we'll look at AES and what that is and how you use it. Then we're going to look at asymmetric encryption, which is RSA. And then we're going to look at digital signatures. But once we've done that, we're not going to stop there. So we're going to explore all of the different primitives that are available to us in the .NET framework. But where the real value is when we start combining them together to do what's called hybrid encryption. So we're taking the best of both worlds from all these different primitives and using them together. Okay, so what is cryptography then? So generally, cryptography is about protecting information. You have a piece of plain text, you encrypt it with some secret encryption keys, and you get ciphertext out the back. So that's what we all commonly think of as cryptography. But actually, there's kind of 4 pillars to cryptography that we want to explore during this talk. So the first one is confidentiality. So that's what we typically think of when we're talking about encryption. You have a piece of data, you don't want someone else to see it, so you encrypt it. But also we've got integrity, which is about detecting whether anyone's tampered with that data or whether it's been corrupted in any way. Then we've got authentication, which is about proving, am I allowed to see this data? So have you got access to see some data? And then we've got non-repudiation. This is being able to prove that it was actually you that sent a piece of data in the first place. So examples of cryptography, you can't wake up in the morning and function throughout the day without being exposed to cryptography in one way, shape or form. So every time you use the internet, anything over HTTPS, it's going to be using cryptography in the background to protect your traffic. Using a cash machine or an ATM, you put your PIN number in, there's a handshake that goes on between that machine and the bank to authenticate you, so that's all using cryptographic protocols. Mobile phones these days, especially iPhones, with the secure enclave chips on there, they're very secure devices these days, as we've seen in the US, where the FBI tried to get Apple to unlock the San Bernardino killer's iPhone, which they refused to do, and then paid some company over $1 million for some tools to help them. But then we've got other areas like cryptocurrency, so Bitcoin, Litecoin, and all of the different currencies that are coming out in that area, and the underpinning blockchain protocols as well, are all cryptography based. I wish I had more time to talk about blockchains, it's one of my favourite subjects, but I only have an hour. But also, picture sort of down here, electronic voting systems are all based around cryptography as well. So once you've registered your vote, can someone go and change your vote and tamper with it, or can you vote twice? So those all use cryptography behind the scenes to help implement them. Okay, so let's start looking at the top of the list then that we looked at, so that's random numbers. So random numbers are very important to cryptography. It's one of the most important concepts we need to get right. And because we use them to generate encryption keys, so we're going to do that, see that multiple times throughout the talk. And there's different ways of doing it in .NET, but the one you don't want to use is that, system.random, because it's not a random number at all, it's very deterministic. So if you don't change the seed that you pass into it, you're going to get the same numbers out. So it's only really good for simulating dice throws and maybe the odd lottery number. So what's better to use is a class called RNG Crypto Service Provider. Now you're going to find that a lot of these objects in .NET, if you're not familiar with them, have got some really ridiculous names, which is why a lot of people tend to overlook them in the .NET framework, because they're not very obvious. So this one is RNG Crypto Service Provider, and that lives in the system.security.cryptography namespace, along with everything else that we're talking about today. And this is very easy to use, and this will be a common theme. All of the things we're looking at are actually very easy to use. They're just not very obvious in the documentation from Microsoft. So to generate a random number, so we've got a small method here. So we pass in what length we want. So typically, we might want a 32-byte random number, which is 256 bits, which is a very common key length to use these days. We create an instance of RNG Crypto Service Provider. We create an array and we call getBytes. We pass in the array that we want filled, which is 32 bytes, for example, and then it gets filled with random data. So that's typically what we're going to use to generate encryption keys throughout the rest of this talk. So moving on then, so the next thing is hashing. So has everyone used hashing before or familiar with hashing? Yeah, the concepts are quite simple with hashing, but they're very powerful what they can do. So a good way to think of it is if you've got a piece of data and then you create a hash code off of it, it's a bit like a unique fingerprint for that piece of data. So you can take in an arbitrary block of data, which is generally in a byte array, you run a hashing algorithm over it and you get a fixed length string effectively out the back of it, which is the hash code for that piece of data. Now, there's kind of a few properties of hashing that are important. So the first one is it should be easy to compute. So generating a hash of a piece of data should be easy. But it should be infeasible to generate a specific hash. So you shouldn't be able to say, for this given for this given hash code, what's the data I need to generate that hash? You shouldn't be able to do that. And it should be infeasible to modify a message without changing the hash. So if you've got, say, a PDF document and you generate a hash of that document, if you go and change just one bit in that document, then the entire hash code should be completely different. So not slightly different, but it'll be completely different. And it should be infeasible to find two identical hashes for the same piece of data, or different pieces of data that produce identical hashes. That's called a hash collision. So that's something you don't want to happen with hashing. So a good way of thinking about hashing then is, when we look at encryption, it's generally a two-way operation. So you have a piece of data, you encrypt it with a key, and then you decrypt it with the same key. So it's two-way. But with a hash, it's kind of like one-way encryption, effectively. So you have a piece of data, you hash it, but then you can't recover that original data from the hash. That's a good way of thinking about it. So there's lots of different hashing algorithms that are out there. So one that's very common and quite old is MD5. This produces a 16-byte hash value. And it was designed by a chap called Ron Rivest in 1991. But in 1996, a hash collision resistant vulnerability was discovered. So it's actually not a very secure hashing algorithm to use these days. The reason we still talk about it is because if you're in the enterprise application development space, you probably might have to work with systems that are much older than you, which still use MD5 hashes. So you still need the ability to be able to calculate them. So they're still used very commonly with legacy systems. Following on from that then, we have the SHA, or Secure Hash family of hashes. These come in different flavours. So SHA-1 and SHA-2 are both in the .NET framework. So SHA-1 produces a 160-bit hash, and SHA-2 produces a 256-bit or 512-bit hash, depending on which one you use. Now, both of those were designed by the National Security Agency in the United States. So naturally, that made a few people slightly nervous. So there was a competition to come up with a new one called SHA-3, because they're very imaginative with the names. And the aim of this competition was that it was going to be a non-NSA designed hashing algorithm. So in the end, an algorithm called KICAC, I think is how you pronounce it, I have no idea how you pronounce it, was deemed to be the winner in 2012. Now, unfortunately, that's not in the .NET framework yet, but I'd expect it to be in there at some point in the not too distant future. So how do we create a hash? Again, it's very easy. A lot of these things are very easy to use. So in the method on the screen, we pass in a byte array, which is our data we want hashed. So that could be someone's password, it could be a PDF document, it could be anything, as long as it's in a byte array. Then we call a static method called create on the SHA-256 class or object, and then we call compute hash, and we pass in the data we want hashed, and then we receive a byte array back, which is our hashed piece of data. So moving on from that then, sort of the next step of hashing is called authenticated hashing. And these are, well, their correct term is hash message authentication codes, or HMACS. So these work exactly the same way as how you generate a normal hash. So you pass some data in, you hash it, you get a hash code back out the back of it. But what you also have the ability to do is pass in an encryption key. So using one of these random numbers that we generated, 32 bytes in length, you can pass that key in and generate the hash code. Now, the good thing about this is the only way you can regenerate that same hash code is if you have that encryption key. So if someone hasn't got the same key and they try and regenerate the hash will be different. So it's good for authentication because someone has to be in the possession of that key. So we'll talk about that quite a bit later on. So as I said, they're used to verify integrity and authentication, which is what makes them powerful. You can have HMACS based on any of the hashing algorithms, so MD5 or the SHA family of hashes. We can use SHA-256 in the remainder of this talk. And the strength is based on the length of the key, so you want a good strong key, which is why typically these days we use 32 bytes, which is 256 bits. You can go higher, but generally at the minute people tend to use 32-byte keys. And the most common type of attack against this is called a brute force attack, and we'll talk a little bit about that in a moment. But again, they're very easy to use. So we have a method here. We pass in a byte array of our data we want hashed. We pass in a byte array which represents our key, so 32 bytes of random data. And we create an instance of the HMACS SHA-256 object, and we pass the key into the constructor. Then we simply call compute hash on that object, passing in our data that we want hashed. And we receive a byte array at the back, which is our hash code. So that leads us on to talking about passwords, or the thorny issue of passwords. So passwords are kind of essential to every system we use. You know, that's the common way we use to authenticate our users. And typically the way people do this, or have done it previously, is to hash the passwords and store those hashes in the database. So has anyone done that in the systems they work on, or seen that? A few hands, probably because people know where I'm going next. So this is all well and good, and it served its purpose for quite a while, but it's actually not that secure. So you can do what's called a brute force attack against that password, which is where you just try billions of password combinations per second, and then eventually you're going to be able to generate the same hash code for a password. Another type of attack is called a dictionary or rainbow table attack, and these are huge databases of passwords, including all the clever ones where you turn the vowels into numbers and put exclamation marks at the end. You know, that really doesn't work. So these rainbow tables exist, and literally, you pass in your hash password, and it's more than likely going to have that password in the dictionary. And the reason why these attacks are easy to do is because generally you use tools like Hashcat, which works using the GPUs on your computer. So GPUs are probably increasing in speed at a faster rate than what normal CPUs are. So people leverage the power of GPUs to try and crack passwords. So it can literally do billions of combinations per second. So a good way to illustrate this, so there's lots of sites like this on the internet. This one's called crackstation.net. So you paste in your hashed password at the top there. That's a SHA-256 hashed password. You put in a little captcha, hit crack hashes, and then it recovers the password for you pretty much instantly. And it's pretty accurate. You can download from dubious places on the internet massive databases of passwords. So it's not a very good technique. So we want to do something that's slightly better. So the next best way, but not the best way, is to do what's called salted password, which is where a salt is effectively another random number, say 32 bytes in length. You append that to the password, and then you hash the password. And that gives you what's called increased entropy. So it increases the password space that you've got to search to try and break that password. And again, that's much better than just doing hashes or even plain text passwords. But as GPUs are getting faster, this can also start becoming susceptible to attacks as well, because you can still test billions of combinations per second. So, a password that's hashed with a 32-byte salt may be secure now, but who knows what could happen in 2, 3, or 5 years as these GPUs get faster. So what we want to get onto now then is the better way of doing it. So it's using something called a password-based key derivation function. Very obvious what that is, isn't it? Or, as it's commonly known, a PBKDF2. So if you want to sound really cool down the pub, you can just talk about PBKDF2s. But actually, the concept is very simple in what it's doing. So we have the password that we want to hash going into the box at the bottom. We have a salt, so we're still going to use a salt, 32-byte piece of entropy. But then we pass in a number of iterations. And what that number of iterations is the number of times that password is going to be repeatedly hashed. And the reason we do this is we're trying to algorithmically slow down the hashing process. So if you think about a GPU can crack, say, 2 billion passwords a second, if you algorithmically slow it down, then maybe they can only check 10 passwords a second. So it makes it much harder for them to do it and less efficient. So a password-based key derivation function is actually an official spec. So I've had to write it down so I can never remember it. It's called the RSA Cryptographic Standard PKCS number 5 version 2. If you was wondering. And it's also published as an RFC document, so it's also called RFC 2898. Again, this is why a lot of people don't tend to know about these things, because they're given very non-obvious names. But the idea is it slows the password cracking process down, so it basically makes it much more secure. But you'd be glad to know it's very easy to use, provided you know what classes to use. So we have to use RFC 2898 derived bytes. Of course, it's obvious. So in our method up here, we're passing in a byte array of our data to be hashed, or password in this case. We're passing in a salt, 32 bytes of random entropy, and we pass in a number of iterations. Create an instance to the class, pass all those 3 things in, call getBytes, and pass in 20, and then we get the resulting byte array, which is our hash. So the reason we pass in 20 to get 20 bytes is the RFC 2898 derived bytes object uses SHA-1 below the scenes, or below the covers, which is, gives you a 20-byte hash, so you don't need to actually extract any more than 20 bytes. So what's a good number of iterations to use? So when I originally wrote this talk, probably a couple of years ago now, I did a little test on my laptop and I did some timing tests. So for 100 iterations, it took 2 milliseconds to hash the password. For 1,000 iterations, it took 16 milliseconds. 10,000 iterations, it took 196 milliseconds, all the way up to 500,000 iterations, and it took 7 seconds, just over 7 seconds to calculate. So one of the things you need to think about as a developer is what is an acceptable amount of time or delay to incur on your users, on your system. So, 7 seconds is very secure, but if you've got someone logging onto a website, do you really want them to wait 7 seconds? They're probably going to go somewhere else. So you have to work out what's an acceptable level. So, sometimes if you go onto a website and you type your password in, it feels like you're waiting a couple of seconds. It's probably because they're using this style of password hashing behind the covers. So, typically I'd say, 100,000 or between 100 and 200,000 iterations is probably a good bet. But you have to think about the context in which you're using these algorithms. Does anyone remember this from a few years ago? I'm not going to ask if anyone was a member, because that would be unfair. But Ashley Madison, they had all their source code and data and lots of other stuff stolen. But one of the interesting things about it was how they took their approach to passwords. So they were actually being quite good. They were using something called bcrypt behind the scene. Now bcrypt is kind of another flavour of password-based key derivation function. It uses different algorithms internally. But it's a similar concept. You have a hashed password and a number of iterations. And that's how they were storing their passwords. That's great. But the attackers also stole the source code to the system, which caused a bit of a problem. Because when they were going through it, they realised that some enterprising engineer at the company, to try and improve the performance of the system, was actually storing local MD5 hashes of the passwords. So when you relog onto a site, it was storing an MD5 hash, which is a lot easier to brute force. And because of this, they managed to recover about 11 million passwords from the system. Just because some engineer probably thought he was doing something good to improve the system, not actually really knowing what he was doing, that actually caused a major problem. So there's a really good article here on that link there, which talks about the story in a lot more detail than what we can do today. It sort of talks about how the processes they went through to do that. Okay, so we've talked about random numbers, we've talked about hashing, authenticated hashing, and passwords. So let's move on to encryption. So the first one we'll look at is symmetric encryption. And the reason the way this works is you have an encryption key, you use that to encrypt some data, and to decrypt that data, you use the same encryption key. So that's why it's called symmetric. Now there's one problem with symmetric encryption is that actually sharing the keys is very difficult to do. So if you've got an encryption key and I encrypt some data, how am I going to get that key to someone else? Now, am I going to email it to you? Probably not a good idea. Should I put it on a USB stick and hand it to you? Probably better, but if someone bashes you over the head with a pipe and steals the USB stick, you're in trouble. So this is one of the problems of symmetric encryption. It's one of the things we can talk about later when we talk about hybrid encryption. Again, just to sort of show this slide again, encryption is a two-way operation. As we said, it's symmetric. You use the same key to encrypt and decrypt, whereas hashing, which we talked about before, is a one-way operation. So the way it works then is we encrypt several bytes at a time, and that data is basically split into blocks. It does some internal encryption operations, does a lot of swapping of all the blocks, but it's a very algorithmic process. It's very fast. And the blocks are typically padded as well. So if you get to the end of the data you encrypted and it's not at the correct size of the block, then it will pad those blocks out. So in .NET, there's 3 encryption algorithms we can make use of. So there's AES, which is the one we're going to talk about most later. Then there's another one called DES and then triple DES. So they're kind of older encryption algorithms that have been broken. The reason they're still in the .NET framework is, again, you might be dealing with legacy systems that have got DES or triple DES encrypted data. So I used to work for a large bank in the UK, and our core banking platform was actually on an AS400 IBM mainframe. So some of the data that it would pass back to us was encrypted with triple DES, so we had to use some of these classes to access that data. But you don't want to go into writing a new system using DES or triple DES. You want to use AES. So AES is an international standard. So well, it's a US National Standards and Institutes and Technology standard, and it was made a standard in 2001. And it was invented by two Belgian mathematicians, so Joan Damon and Vincent Riemann. And the original algorithm they came up with was called Rijndael. But then Rijndael was what originally won the competition and became the standard, and it's known as AES as we know it today. So to use it, there's several things we have to do to pass into AES to make it work. So we have our plain text at the bottom, so that's the data that we want to encrypt, that we want to make secret. We have our key, which we pass in as well. So that could be 128 bits, 192 or 256 bits in length. So we're going to use 256 bits. Then we also have this thing called an initialization vector, which is 16 bytes of random data that you have to pass in. And the reason we do that is because the data is split into blocks and it does operations between those blocks. You kind of need a bit of seed data to get it started. It's kind of like a kickstart to the algorithm. So we pass in 16 bytes to do that. Now those 16 bytes aren't secret, they're not a key. So you store them along with your data. But it's something you need to be aware of. So in .NET, we have two flavors of AES, which are most commonly used. There's AES Managed and AES Crypto Service Provider. And they both do exactly the same thing. So AES Managed is a native .NET implementation of AES. And there's nothing wrong with it. It works, it's fine, it does its job. But it's not been certified with something called FIPS 197-2, which is basically a certification scheme that the algorithms go through. And what that gives you is then, if you're certified, you know that if you receive any encrypted data from another system, say written in Java or an IBM mainframe, you're going to be able to decrypt that data and vice versa. So AES Managed hasn't gone through that certification scheme. It'll probably work, but it's not certified to work. So the alternative then is AES Crypto Service Provider. And that uses the underlying Windows crypto platform, and I'm not quite sure how they've done it in .NET Core, but it's going to use something else, I don't know what. So to use it, again, it's fairly straightforward, and all the code which I said about on GitHub at the beginning, all of this is in there, so you can just steal it. Not steal it, borrow it, use it. It's open source. So we have our encrypt method, and we pass in a byte array of our data to encrypt. So that could be, a small bit of text, or it could be a large document that's been split out into a byte array. We pass in our key, which is 32 bytes in length, and then we pass in our 16-byte initialization vector. Then we simply create an instance of the AES Crypto Service Provider class. We pass in the key and the IV, and then we create a memory stream and a crypto stream, because it's all stream-based, how it works. So you can pass in quite large pieces of data. And then we call write and then flush on that crypto stream, and then we can pull that data back out, which gives us our encrypted byte array. So it's quite straightforward to use. And to decrypt it, we pass in the same information, our data to decrypt, our key and our initialization vector. We create the AES Crypto Service Provider class, create the streams, call write on the streams, and then that data gets decrypted. So it's nice and straightforward to use. Okay, so following on from symmetric encryption, we have asymmetric encryption. So I'm sure everyone's heard of RSA, have they? Yeah? So it's a same premise, but it works in a different way. So in asymmetric encryption, we have two sets of encryption keys. You have a public key and a private key. And I'll talk about those a bit more in a minute. So RSA was invented by RSA Data Security Incorporated in the States by three guys, Rivest, Shamir, and Edelman. And the way this works compared to, say, AES, AES is very algorithmic in how it works. It splits data into blocks, it does encryption operations, it swaps blocks around. So it's very, what we typically think of as a computer algorithm. Whereas RSA is more mathematical in how it works. It's all based on modulus arithmetic. So at the moment, the current minimum recommended key length for RSA is 2048 bits, but you can use 4096-bit keys as well. One of the downsides of RSA is because it's mathematical and it's all based on modulus arithmetic, is you can only encrypt up to the size of the key. So you're limited on how much data you can encrypt in one go. Which seems like a bit of a limitation, but as we'll see later, it doesn't really matter, because when we start combining a lot of these systems together, we get a lot of benefits. So the way the key works then is it's all based on prime number factorisation. So if we have this simple sum up here, so 23 times 17, either in our heads or on a calculator, we can quickly work out the answer. It's 391. If we go the other way, so if I was to ask you what two prime numbers make up 5,963, does anyone know the answer? No one's got it yet, that's fine. So it's 67 and 89 multiplied together, and that's kind of the underlying premise of how the security of the keys works, but the prime numbers are huge, massive prime numbers. So in this sort of case, our public key is the 5,963, and the private key is the 67 and 89 numbers. So the private key, you don't want anyone else to know, that's your own private key. But the public key, you can put it on the internet, you can post it to people, email it. It's okay for anyone to use. So how does this work in practice then? So first of all, in .NET, we want to generate a new key or a new set of keys. So you create the RSA Crypto Service Provider class, you pass in the key length that you want, so in this case 2048-bit keys. And then you call export parameters passing in false, gives you your public key, and then you pass in true, and it gives you your private key. So in this example, we're just storing it in memory. So one thing you have to be aware of is how you're going to secure and protect those keys. So one way is you can generate certificates and store them in certificates, or you can use things like Azure Key Vault or hardware security modules to do that. So is everyone here work on Azure or Azure, depends on where you come from? No? A few people, okay. So Azure Key Vault is effectively a hardware security module or an abstraction over a hardware security module, and it's a piece of hardware which is designed to secure or to store encryption keys very securely. So if anyone tries to tamper with the hardware security module, then it wipes itself. So Microsoft has data centers full of these things. They're based on the Thales N-Shield hardware. So highly recommend playing around with that. It's actually very cheap to use on Azure. It costs cents per key. It's really cheap.
Can be used on VMs and web apps?
What, from code?
Not from code. It's nothing, no.
Okay, I mean, there's a full set of APIs, so you can use it and use it from what you want. Okay, so to encrypt some data then, so we pass in a byte array of our data to encrypt. We create the RSA Crypto Service Provider object. We import our public key, because when we encrypt data, we use our public key to encrypt it. And then we call rsa.encrypt, and then we get our encrypted data back out. So to decrypt the data, we pass in our data to decrypt. It's like a typo on the slide there. Create the RSA service provider object. We import our private key this time, because to decrypt the data, we need to use our private key. Then we just call decrypt on the RSA object, and then we get the original data back. So if we think about how this is being used in practice, so if I want to send, say, you some data, I would use your public key to encrypt the data, and then you decrypt it with your private key, because you're the only person that knows that key. Okay, so moving on from asymmetric encryption, we've got digital signatures. So earlier on when we talked about the 4 pillars around cryptography, one of them was non-repudiation, so being able to prove that it was actually you that sent a piece of data. So this is where digital signatures help us out with that. And these are used all the time. So has anyone used DocuSign website? Yeah, a few hands up there. So DocuSign is a good example. So it's a way of signing contracts between 2 parties. So we use it at Pluralsight when we sign an author agreement for a course. We do a 2-way signature thing with DocuSign. And that's using digital signatures behind the scenes. So that if, say, either me or Pluralsight disputed anything in the contracts, well, you can't, because we've both digitally signed that contract. So to do digital signatures, we kind of need 3 different things. So we need key generation, which is exactly the same as what we did for RSA. And we need a sign-in algorithm and a signature verifier algorithm. So the way this works then is you have a large piece of data, as denoted in the green box at the end there, and then you create a hash or a HMACS of that data. So you end up with a 32-byte hash of that piece of data. And it's actually that hash which you then create a digital signature of. So because digital signatures in .NET are based around RSA, you've still got that limit of how much data you can encrypt in one go. So you tend to generate your signatures off of hashes of other pieces of data. So if we look at this as an example, so we've got Bob wants to send a a digital signature. So what he does is he creates a digital signature using his private key. So remember before when we used RSA, we encrypted with a public key and decrypted with a private key. This is the other way around. So we create the signature using your own private key. You send the message over the internet to someone or the intergalactic spider's web. On my diagram, I'm not very good at art and design, I'm afraid. So you send that image, that digital signature to Alice at the bottom there, and then she uses Bob's public key to verify that signature. So if anyone else other than Bob created that signature, then the signature won't verify at the end. So Alice will know that that message didn't come from Bob. So again, to use it, it's quite straightforward. So we generate a set of keys, exactly the same code as what we saw a little while ago. And then we want to use a class called an RSA PKCS1 signature formatter. Wonderful bit of class naming by Microsoft there. So what we do, so we create the RSA crypto service provider, then we load our private key into it, so our key's all ready to use. And then we create the RSA PKCS1 signature formatter, try saying that after a few beers. And we pass in the RSA object. We tell it what hashing algorithm we want to use, so SHA-256 in our case here, and then we call create signature of the hash that we've passed in, and that will give us back a byte array with that digital signature in. So now if we want to verify that a signature is valid, so our recipient is now going to check the signature, we pass in the hash of the data that's been signed, and we pass in the signature. Create the RSA crypto service provider object, load in the public key, because that's what we're going to use to verify the signature. And then we call RSA PKCS1 signature deformatter, set the hashing algorithm to SHA-256, and we call verify signature. And we pass in the hash of the data that was originally signed and the signature, and it'll either return true or false. True, it's a valid signature. False, it's not. Discard it. Okay, so if we do a quick recap of the 4 pillars, and then we'll look at how we've satisfied those 4 pillars. So confidentiality, we talked about AES and RSA, so that's typical encryption that we all know and love. Integrity, we talked about hashing, and we used SHA-256 as a hashing algorithm there. Authentication, we used HMACS or hash message authentication codes using SHA-256. And then we talked about non-repudiation using digital signatures, so being able to prove that you're the actual original sender of a message. So those are all great and very useful in their own right, but really what we want to do is start using these things together to do something more powerful, which is where we get onto hybrid encryption. Okay. So we've already said that RSA has a limit on the amount of data you can encrypt in one go. It's a very slow mathematical process, so you can't encrypt or decrypt anything bigger than the size of the key. AES, on the other hand, is very fast and very efficient at encrypting data, but sharing the keys is hard. It's very difficult to get a key from one person to the other. So what we're going to start off by doing is combining RSA and AES into a hybrid scheme. So we're going to build this up bit by bit. So what we're going to do first then is we're going to use AES for encrypting our data, and then we're going to use RSA for encrypting our encryption key. So if we walk through this, there's a few examples. So first of all, we're going to generate a session key. So it's just a 32-byte random number that we're going to generate. Then we're going to use that session key to encrypt our data using AES. So that's our data encrypted, ready to be sent. And then we're going to use our recipient's public key to encrypt that session key. Then we send the whole lot over to the recipient. And then for them to recover the message, they have to use their private key to decrypt the session key. And then once they've recovered that key, they can then go and decrypt the original data, and that gives them the original data back. So in terms of the data that we're sending across to the recipient, so we've got the RSA encrypted session key. We have an initialization vector, because remember we need 16 bytes to jumpstart AES. And then we have the AES encrypted data. Everyone followed that so far? Cool, let's walk through a couple of examples. So Alice wants to send Bob a message. So she starts off by generating her session key, and then she generates her initialization vector. She encrypts her data with AES, so that's her data now protected. She then encrypts her session key with RSA and posts the whole thing over to Bob. So Bob now wants to read that message. So he decrypts the session key using his private key, because only he knows that private key. He then uses that decrypted key and initialization vector to recover the original message, and then he can read the message. So meet me at noon below the clock tower, wear a red rose in your button, very spy thriller. So now Bob wants to send a reply back to Alice. So he creates a new session key, because you never reuse the same keys, you generate new ones. He creates a new initialization vector, and he then encrypts his reply using that session key. He then, using Alice's public key, encrypts the session key, and then sends a whole lot across to Alice. So she now uses her private key, because again, only she knows her private key, to decrypt the session key. She then uses that and the IV to decrypt her message, and then she can read it. So I will meet you, I will be wearing a blue hat and red boots. So she's very fashion conscious. So that's great. So we've satisfied a couple of problems. So we've satisfied the fact that RSA can only encrypt small amounts of data efficiently. And we've also fixed the problem where getting a symmetric key from one person to the other, which was hard. We've now had a better way of doing that. So now what we want to do is we want to make sure that whoever receives that message is confident that someone hasn't tampered with the data or it's been corrupted as it's been sent. So we want to know, is that data actually intact and not being fiddled with? So we do exactly the same process as what we did before, but before we send the message to the recipient, we also generate a HMAC of the ciphertext and the IV concatenated together. And the reason we use a HMAC is because we can then use that AES session key to generate that hash. So the only way you can verify that hash is if you've recovered the key on the other end. So then on the other end, the recipient uses their private key, they decrypt the session key, they can decrypt the text, and then they can use that decrypted session key to verify the hash. If the hashes are identical, then great, the data's not been corrupted. If the hashes are different, then you discard the message because someone's either tampered with it in transit or it's been corrupted over the wire. So our data that we send across the wire then looks like this now. So we have an encrypted session key, we have an initialization vector, we have our AES encrypted data, and then we have a HMAC of the encrypted data. So that's great. So now what we want to do is we want to make sure that it was actually Bob that sent the message in the first place and not Jeff, evil Jeff. So again, everything we've done before we're still going to do, but before we send the data, we're going to use our private key to create a signed hash of that hash that we created previously. That's using our private key. So as the sender, only I have that private key. So if anyone verifies the signature on the other end, it can only have come from me, unless someone's stolen my key. So again, if we look at what that looks like, so when we send that data, we have the RSA encrypted session key, the initialization vector, the AES encrypted data. We have our hash of the encrypted data, or our HMAC of the encrypted data, and we have a digital signature of that hash. So the person on the other end has to verify that signature. They then have to use their private key to decrypt the session key, which they then use to decrypt the data and then read the message. So actually what we've done, so we've used all of these very simple primitives in .NET to give us something quite powerful. So we can securely send data from A to B using public and private keys, because that makes the key sharing problem a lot easier. But we've used the efficiency and the speed and power of AES to encrypt our data, and we've made sure that the data hasn't been tampered with over the wire or been intercepted, and we've also made sure that we're sure that it was actually Bob that sent that data in the first place. So that's quite a powerful concept. Oh, I've just talked over that slide without showing the slide. But that's effectively recapping what we've just done. Has anyone's brain melted yet? Okay, so that's effectively what I wanted to cover. There's quite a lot to it. As I say, if you don't quite understand all of it right now, that's absolutely fine. Treat this talk as kind of the art of the possible, so you kind of had a flavour of what you can do with these sorts of things. If you do want to watch my course, it's about 3 hours long, or 4 hours long. It covers the same topic, but it goes into a bit more detail and a bit more depth, and it walks you through all the code samples. So it's a slower way of going through it, which is good. Where we talked before about the difficulties of storing RSA keys, so this course here shows you exactly how to do that. And again, all the source code for that is available on the course, so you can just take it. And that shows you how to store keys in the Azure Key Vault if you're using Azure. I'm sure AWS and Google Cloud have very similar things in them as well. I've just not used them myself. But that's a good way of securely protecting your RSA keys. So feel free to use the code, steal it, do what you want with it. Use it as a basis for your own security in your own systems. I encourage people to do that and take a look at it. And again, the slides all on GitHub as well. So if you want to refer back to the slides, you can just go and download them from there, along with the slides for all my other talks. So a bit of further reading. So I mean, when I first started looking at this sort of stuff years ago, it's an absolutely fascinating subject, cryptography. So I've got 3 book recommendations here, should you want to go in more detail on it. So the first book is called The Code Book by a guy called Simon Singh. It's a very small book. It's kind of a novel size. I read it on holiday once, my wife's horror. But it kind of covers the history of encryption and cryptography from sort of ancient day up to sort of modern day. So it's kind of a historical document more than anything. It's good fun to read. Everyday Cryptography covers a lot of the things that we talked about today in hybrid encryption, but it also has lots of examples about where encryption and cryptography is used in real-world scenarios. So how does a TLS handshake work when you use your browser? How do cache machines authenticate you? It goes into more detail on that. The last book is called Applied Cryptography. Now, this is the book that was released in the early 90s. This is the book that the NSA tried to ban at the time, because this was at a time when encryption was considered a munition, a weapon. But it's a fantastic book, but it's very mathematically heavy, so you have to be into that kind of thing. It doesn't cover AES because it came out before AES was written, but if you want to have a good insight into how these algorithms have evolved over time and how they work, then it's a great book to read. So thank you very much. I hope you've enjoyed it.